Good afternoon. I'm Jill Pfeiffer, and it's my pleasure as the president of AMS to welcome you all to the inaugural Maryam Mirzakhani Lecture. The AMS Council established the Maryam Mirzakhani Lecture to honor this first woman and first Iranian to win the Fields Medal. She won the medal for outstanding contributions to the dynamics and geometry of Riemann surfaces and their moduli spaces. Maryam Mirzakhani had shown great promise in and passion for mathematics, even as a high school student in Iran, winning gold medals in 1994 and 95 in International Olympiad. But competition success does not predict research success, as Kurt McMullen, her PhD advisor, once remarked. What truly distinguished Mirzakhani, in Kurt McMullen's words, was her ability to generate her own vision. Indeed, her spectacular PhD thesis contained 3 breakthrough results, including a new proof of a conjecture of Witten proven first by Kontsevich. From there, she went on to the groundbreaking work that earned her Fields Medal recognition. Maryam Mirzakhani died at the age of 40 in 2017 after a several years-long battle with cancer. And many tributes to her life and to her work have been collected on an AMS website, and I invite you to start there to learn more about this remarkable mathematician. And now I'm going to turn it over to Robin Newmeyer to introduce our speaker.
It's a great pleasure to introduce Professor Tatiana Toro, the speaker for the inaugural AMS Maryam Mirzakhani Lecture. Professor Toro is a Craig McKibben and Sarah Murner professor at the University of Washington. After receiving her PhD at Stanford in 1992, under the supervision of Leon Simon, Professor Toro held positions at the IAS, UC Berkeley, and the University of Chicago before joining the University of Washington in 1996. She's held memberships and visiting professorships at the Radcliffe Institute for Advanced Study, Harvard, University College London, MSRI, and UC Berkeley. Professor Toro was inducted as a fellow of the AMS in 2016 and was inducted to the Columbian Academy of Sciences in 2017. She was a speaker at the ICM in 2010. She's the recipient of numerous awards, including 2 Simons Fellowships, a Sloan Fellowship, an NSF postdoctoral fellowship, and a Guggenheim Foundation Fellowship. Professor Toro's research lies at the interface of geometric measure theory, harmonic analysis, and partial differential equations. Her work has been foundational in the study of the relationship between the geometry of a domain and the properties of solutions of partial differential equations on that domain. Professor Toro has supervised a number of graduate students and postdocs, and in 2019 was awarded the Landahl Distinguished Graduate Mentor Award. She co-organized the first and second Latin X in the Mathematical Sciences conferences in 2015 and 2018. Please join me in welcoming Professor Tatiana Toro, who will speak to us today about differential operators and the geometry of domains in Euclidean space.
Thank you, Robin, for the introduction. And first of all, let me say that it's a very big honor to be here as the inaugural speaker for the Maryam Mirzakhani Lecture. She was an extraordinary mathematician, and we're here to celebrate her life, her contributions, and her legacy. Thank you. So as Robin said, we're going to talk a little bit about all those areas where I've worked. And in particular, if you read the sampler, you saw this picture. And so I'm going to give you 2 words, rough and smooth. And I'll ask you to try to put them into the different objects, qualify the objects. And I think we will all agree that the mountains look rough and the water looks smooth. And I'll let you decide what you think of the trees. But it's kind of, so we know how to apply the adjective, but what if I ask you, what does describe the adjective? So that we're clear, we're going to look at another picture. This one. If I told you here one of the objects is rough and one of them is smooth, you will say yes, of course, and you all know which one is rough and which one is smooth. So what I would like to do today is explain a little bit, in my vocabulary, you might have a different one, what rough and smooth mean. And of course, I'll give you the motivation, I'll give you where I come from, but really I am trying to find ways to describe in mathematical terms these two objects. And when I think of the objects, I want you to think of what's inside. So on the red thing on your right, I would like you to think of what's inside the shiny, maybe glass ball. And I want you to think what's inside the stone, okay? Okay, why? So the question is, how do we describe roughness or smoothness? What mathematical tools come into play in this talk? I'm sure if you're in an algebraic geometry, you'll say something very different. This is not an algebraic geometry talk. Well, there will be tools from functional analysis, from partial differential equations, from harmonic analysis, from potential theory, and from geometric measure theory. And I'm very aware that most of you might not even know what this means. So I want you to do me a favor. There will be sometimes words that you don't understand. I want you to look at the pictures that come with those words. And hopefully the pictures will explain what maybe the words don't, okay? Let's go back to the lake and the mountain. And the question is, can the temperature distribution distinguish between the physical properties of the mountain and the lake? And of course, I'm taking some literary freedoms here. Maybe not everything I'm saying is 100% precise, but it's rather accurate. And more precisely, can the boundary behavior of a harmonic function, what's a harmonic function? My temperature distribution. Distinguish between them or between a bubble and a snowflake. And I will show you a bubble and a snowflake in a minute in the next picture slide, so you see if you think that's the case. And so what's the relationship between the geometry of the domain? The mathematical question is, what's the relationship between the geometry of the domain and the properties of the solutions of partial differential equations on that domain? So this is a question. Are these objects rough or smooth? So you look at the mango, and I'll ask you in a second, I'll take an anecdote. Why did I put the mango or the Romanesco? I was at a supermarket years ago, and kids are always asking their parent, there was a kid asking their parent in terms of the vegetable, is this yummy or yucky? So depending on what you think of rough and smooth, I'm asking you if it's a yummy or a yucky. So the mango is relatively smooth. The sub-bubble looks smooth. The Romanesco doesn't look as smooth. And then the snowflake, and I want you to look at the edge that's flat, doesn't seem as smooth. So here I think we could agree. I'm going to show you a set of other pictures. Please listen to, there's some that I'm going to explain a tiny bit more so you see which ones I really mean. So the first thing that you see is a stellar, the dodecahedron. And if I ask you, is it smooth or is it rough, you can say, well, there's pieces that are smooth and pieces that are not as smooth. They're rough. You know, there's edges and there's points. And let me look for a minute at the sculpture. So I was looking for the picture to illustrate something that's called a Lipschitz domain, which you will see later. And I did a Google search, and Lipschitz appeared. For those of you in the field, you might be thinking, oh, there's something funny. So Jack Lipschitz was a Cubist sculptor, and all of his sculptures look like this. And what do I mean by this? You see, there's very smooth, flat pieces, and then there's edges that are like corners, and then there's points. And that's your definition. So think of the stone that this sculpture is made out of. That's the best Lipschitz domain you've ever seen. All his sculptures are Lipschitz domains. Okay. Now, the four-cornered Cantor set. What do I want you to see? I start with a square. I cut in 16 equal squares, leave the corners. Repeat, 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 repeat. And what I want you to visualize is the white page minus the dust. And I ask you, is that a domain? a smooth domain or it's not smooth. And in the case of the Sierpinski gasket, I ask you to do the same thing. You see, you repeat, repeat, repeat. You put that dust in this room, and what you get, is it smooth or not? Now maybe we're not so sure what's rough and what's smooth, but just to show you that it depends on how we're looking. So I need to give you the tools by which we're going to look at these. Okay, so my model domains. For me, this is a smooth domain. What is this? Please look at the interior of the circle. That's my domain. This is a Lipschitz domain. Think of the sculpture. You see something that has smooth pieces and corners. A few corners, not too many. A snowflake. What's a mathematical snowflake? Some of you have seen the Van Gogh curve. You iterate this picture, you keep on going, the final product is that. And now the complement of the four-corner Cantor set. So these are my model domains, and we are going to try to find the mathematical tools to distinguish between them. You have some mathematical tools. So these only requires calculus, maybe calculus, the first calculus. Some of the things we're going to say at the beginning will change in a second. Okay, so geometric properties of the model domain. Omega is the inside of the circle, the inside of the snowflake, the inside of the Lipschitz domain, or the complement of the four-corner Cantor set. The surface measure, which is either the length, in the case you saw in the picture, it is the length of the boundary, but if I were in space, it will be the surface of the boundary. Well, when you're smooth, it is finite. When you're Lipschitz, if it's finite. When your snowflake is infinite. What do I mean? If you are an ant and you want to go from one point of the snowflake to another, you will never make it. It's infinitely long, that curve. You'll never get there. You're not an ant, I guess that's not your problem. And for the complement of the four-corner Cantor set, so the boundary is this dust. So you might be thinking, what on earth does she mean by the length? The length is a generalization of length and tells us that this is of dimension 1, and it turns out it's finite, okay? Now, tangents, when you teach calculus and you teach your students about tangents, they look on the calculator, they do like that until it looks like a line. So smooth domains have tangents. Lipschitz domains have tangents almost everywhere. Snowflakes don't have tangents, and the four-corner Cantor set, the complement doesn't have tangents, okay? So these are some differences. I need to give you more tools. Now, let's go back to, I'm assuming all of you took a very basic topology class, and you remembered what an open set is. So I'm going to draw a picture of an open set. If I have my domain omega, the blue thing, and I take a ball around any point on the boundary, and I look at this purple intersection, we say it's open. It means that for every point inside, I can find this little red ball around. That's open. In this field, we cared about being quantitatively open. So let me draw a picture. The pictures are courtesy of one of my collaborators who you will meet later. This is a quantitative openness. In each one of these balls centered at the boundary of my domain, I want to find, and I was told this was the best way to do this, I want to find for every point here, I want to find a ball of comparable radius. So if this is R, this red ball has radius CR, and is completely contained in the purple intersection. Okay? This property is called corkscrew. Think of your corkscrew, the one that you use to open a wine bottle, and when it goes around, somehow, the point is thinner, the rest is thicker, and it's like there's little balls around there that are going directly to the center of the cork. Okay? So the tools, I'm giving you the tools to distinguish between the model domains. Okay? Let's go back. Let's stare at the model domain. So for the minute, look at, I care about the quantitative question. So I'll give you a hint. I'm going to ask you, of the model domains, which ones satisfy the interior corkscrew? So if you look it's fairly clear that the smooth domain does, the Lipschitz domain does. A little bit more carefully, you find that the thing that's inside the snowflake does. And with more work that we will not do here, it turns out that the complement of the four-corner Cantor set does. Now, what about if I look at the same question but the exterior? Well, inside and outside of the smooth domain is more or less the same. Inside and outside of the Lipschitz domain or of the snowflake is more or less the same. What about the complement of the four-cornered Cantor set? Well, there's no exterior. The interior, there's nothing in the interior of the complement. So that's why we have these things. OK, so what do I want you to do? I want you to focus on the last two lines here. And notice that from this lens, it's like, think of, so my father is a pathologist, and my mother is one too, and they use lots of the microscope and lots of different lenses to be able to see different things. And I always think of what I am doing here is I'm presenting to you the lenses of my microscope to tell you whether these domains are the same or they're different. So first lens is, I will refine these ones, but for these two in the bottom, you realize there's a difference. There's a no here. OK. I give you another lens, slightly different, one that is really useful in PDE. Remember, the connected set, a path-connected set, is a set such that you can join any 2 points by a path. Let's think what a quantitative version of that is. Well, I can join them by the path, but this path can be covered by lovely balls. There's not too many of them, and they have this shape. And if I tell you what the shape is, it's going to be complicated. I want you to stare at the picture, and you see what it means. There's not too many. The further away balls are bigger. The nearby are smaller. OK? So that's called a Harnack chain, and that's my quantitative version of path connectedness. Once again, think of the model domains, and let's see what happens to the model domains. So the Harnack, they all have Harnack chains. So at this point, we only have one way to distinguish is this exterior corkscrew. And what we would like to do is see if, from the PDE point of view, there are differences between these two domains, and if those differences are just a coincidence, or there's something more there. Okay? So before I go there, I'm going to put some of all these conditions about path connect, uniform openness and quantitative path connectedness in one definition. So we're going to call a uniform domain a domain that satisfies the interior corkscrew condition and the Harnack chain. And because sometimes it's better to understand the definition if I show you a picture of what's not a uniform domain, let me give you an example. So this thing here is not a uniform domain. And why? Because this point does not satisfy the corkscrew. There's a cusp, and there's no way I can put in here or in here a ball of comparable radius with a fixed constant. And here, there's no Harnack chain, because to go between this point here to this point over here, I will need too many balls, OK, if they're going to have this property. So I'm looking for something that doesn't look like this. And just to summarize, and now you have the idea. Oh, sorry. We'll do that box in a second. I realize we're going to do now is we're going to do at the PDE. OK. Everybody takes a deep breath, in particular those people who don't like, did measure theory and thought I will never again have to do an analysis class. My suggestion is go to a safe place. For example, the lake and the mountain, and think of the temperature, and think that the temperature both of the lake and the mountain might be are governed by some law of mathematics, in that while we think of the water as a homogeneous medium, we should think of the mountains as inhomogeneous. I mean, they're little rocks, there's dirt, and so if I were to describe the temperature there, I will have to take into account those differences of materials, okay? That's what the next slide says. It just has a fancy notation, but if you never did a PDE, just think of that for a minute while I go through this slide. Thank you. Okay, so the Dirichlet problem. I have a domain in Rn, is a bounded domain, the mountain or the lake. I take a continuous function on the boundary of this domain, and I am interested in solving a partial differential equation. What do I mean? I want to find a continuous function that satisfies this number 1 here that doesn't tell you anything because I haven't told you what L is. Well, L is the divergence of a matrix A times the gradient. And the matrix A is uniformly elliptic, which means that funny thing there means that the eigenvalues are bounded above and below, are positive and bounded below by a number greater than 0 and above by a capital lambda bigger than 0. How should you understand that? Well, if A is the identity, L is the Laplacian, which is the sum of the second derivative, is something that you might have seen. The Laplacian describes a homogeneous medium. The L should be understood Laplacian in an inhomogeneous medium. Think of A as something describing the mountain, what the mountain is made out of, and there are discontinuities there, okay? You might have, how come she's differentiating something that has discontinuities? A leap of faith. Let's not worry about that, okay? And the solution, the solution describes the temperature in steady state where the boundary's temperature is F, okay? So this is, from the mathematical point of view, this is the things we're looking. Now, I'm going to give you properties of these solutions. I'm going to ask you to believe that in some, you'll see. I'm going to give you properties. The first thing, so the maximum principle holds. What's the maximum principle? The maximum principle is the thing that tells you that when you drink your coffee, you drink it from the edge because that's what's cooler. You put it in the center, it got cooler at the edges, okay? Same thing with the soup, okay? The Georgi-Nash-Moser proved that the solution is always Holder continuous. Remember, inside. We wanted a continuous function, at least I have it continuous inside. This is a very, very big deal in PDE. Additional smoothness of A, if A, you can differentiate A, or it tells you U is even nicer. That's great. But, so what I want to focus on is, remember, in all of these domains, I've been focusing on the edges, so on the boundary. So is there anything about the behavior of the solution U at the boundary that tells me something about the geometry? And does the geometry of the domain tell me something about how U behaves at the boundary? No. It depends on the boundary, of course. So if omega, we say that omega is a regular domain. This is, in some sense, the most difficult definition, the most abstract. If for every continuous function, you can find a continuous solution, and it's continuous all the way to the boundary, and in the boundary is exactly F. Okay? That's the definition. Now, your question is, okay, great, but how do I know? If I give you a domain, how do you know if it's regular? So in 1924, Wiener, a probabilist, characterized all the regular domains for the Laplacian. This is a spectacular result, which is quasi-impossible to use. But it tells you if this happens, then it's an if and only if. But notice I said the Laplacian, and then Liebman, Sampakian, Weinberger in 1963 said that the same thing was true for the other operators. Okay? So let me give you some examples of regular domains, and you guessed. There we go. All of these domains are Wiener regular domains. So I can solve the Dirichlet problem here And if you have been paying a lot of attention, something happened. So this is one of those tricks, like, except that I cannot put the two things together, where I say, what's the difference between this picture and the last time you saw this picture? I changed something. I changed quasi-ball. So before I had snowflake, and now I put quasi-ball. So if you're not an expert, think snowflake. If you're an expert, think quasi-ball, the quasi-conformal image of the unit ball by a global quasi-conformal transformation. Okay? So that's another example, but all of those lovely things are regular domains. Great. Let me tell you something about regular domains. I need to keep on going to be able to tell you, okay, what's the other tool? I am introducing you the other tool, the other lens. So by the max, if omega is regular, so think of just my model domains. If it's regular, by the maximum principle and the Riesz representation theorem, I can write every solution as an integral against the measure. Okay? So there's a formula. The solution of that Dirichlet problem is the function f I started with against this measure, and is a probability measure. It's called the elliptic measure when is at L, and it's called the harmonic measure when L is the Laplacian. I'll tell you what they are. But so why is it in blue? Because it's like the building block. I want you to think that these, and I'm going to go, I want you to think that omega L is the building block for all the solutions. So if I understand omega L, I understand the behavior of all the solutions at the boundary. So I'm going to drop the solutions, and I'm going to focus on omega L. Why? Because I started as a geometric measure theory. Omega L is a measure. Measures are my friends. I like them. Now, there was this bullet in there that tells you if the domain is nice, connected, for example, it doesn't matter what my omega L has an x, a y, or where the pole is. And so we're going to drop it. We can simply talk about the properties of the family of measures. Okay, let me explain a little bit, at least in the case of the Laplacian, who this, the harmonic measure is. So I stole these pictures from one of my former students' website. He's aware of it, so it's not full theft, thank you. But so omega x of E is a subset of the boundary, is the probability that a random walk starting at x will first hit the boundary at a point in E. Okay? So, and when I have the Laplacian L rather than the Laplacian, think of an inhomogeneous version of these. Okay? So it's a very concrete thing. The harmonic measure is a canonical measure used by probabilists, by people in PD, in potential analysis. So it's almost as canonical to a domain as a surface measure, and sometimes surface measure doesn't make sense, but the harmonic measure does. Okay? So I am going to use this harmonic measure and the elliptic measure to try to differentiate this thing. So, I'm seeing something strange. Okay, so can harmonic and elliptic measure distinguish between smooth domains, Lipschitz domains, quasi-balls, and the complement of the four-corner Cantor set? That's a question we've addressed, but that's not the one I want to focus on. I want a subset of that. Can the relationship between harmonic or elliptic measured and surface measure distinguish between these three types of domains: smooth, Lipschitz, and the complement of the four-corner Cantor set? Why did I drop the snowflake? Because there the surface measure was infinite. That doesn't make sense. Okay, forget it. Okay, I'm going to give you one more property of a measure, and I'm going to, you see there's the word relationship. I need to tell you what does it mean for a relationship of between two measures. So that's the content of the next two slides. So the surface measure, we say that a domain is Alford's regular if there exists a constant such that the surface measure, a domain in Rn, the surface measure of the ball centered on the boundary grows like Rn minus 1. If you're a geometer, think it has Euclidean volume growth. It grows like it will grow if you were the subset of Rn minus 1. It's a measure of regularity of a measure. Really horrible sentence, but that's what it is. Okay, let's go back. Now I'm not going to ask you to check, but between the smooth, the Lipschitz, and the complement of the four-corner Cantor set, it turns out that their surface measured is always out-force regular. They're all uniform, and the only difference still is that there's no corkscrew. Okay, so you're going to be thinking the surface measure is useless since I'm trying to distinguish. Wait for a minute. We need to get to the harmonic and to the elliptic measure, okay? So for an alpha, so they're all, if you stared here, I'm gonna ask you to please stare at the top lines. If you stare there, for an alpha's regular uniform domains, does the existence of exterior corkscrew balls tell you anything about the relationship between sigma and omega L? And maybe this sounds like a weird condition, but when you are the lab scientist and you're trying to find correlations, you always do things like that. You have hypotheses, maybe this is what influences that, and that's what we're doing. Could it be that this difference here, I can see it with my sigma and my omega L? And can this relationship help me predict whether I have an exterior ball? And I want you to think of it. I am saying, I have this PDE, maybe one that you have never seen, and I'm asking, does this PDE, does a property of this PDE tell me something about the geometry, something that I understand? I'm sure you all understand having a ball outside. I mean, that's something that we can all visualize. How can they be related? Okay, so that's one of the questions we want to answer. And you might want, why do we care? I will explain that or try to, I need to make my case. Why are you going to keep on funding me? And then, I talk about relationship, but what sort of relationship do I want between measures, okay? Okay, why do we care? Well, we care for the following thing. We have two reasons. We have a geometrical reason, and is that, and I will explain why this matters. David and Jerrison in 1990 proved that if you have an alpha's regular uniform domain, and it satisfies this exterior corkscrew ball, then for every point, there will be a picture. For every point and for every radius, if you think of this intersection of the boundary and this ball, you can construct a Lipschitz domain, omega prime. The distance of that funny point that I had drawn before to the boundaries roughly R. There's the intersection with the boundary is big, but in particular it means I can construct this yellow domain. Okay, so this yellow domain is a Lipschitz domain, sits nicely inside the intersection of the ball and the domain. It has the boundary touches in a very big place. And for a harmonic analyst, you say, oh, great, now I know how to do things. That's all what I needed. And so for us in this field, this is our gold standard of smoothness. Okay? If I have a domain and I can put Lipschitz domains inside that touch in a very big piece of the boundary, I can do basically anything that I could do for a Lipschitz domain, I can do for this domain. So you see, in some sense, what this is telling me is that this ball outside makes my weird-looking domain behave almost like a Lipschitz domain, which is smooth in this area. Okay? So I'm happy. That's one of the reasons we care. Now, why do we care analytically? Okay, and now, so I see you're not seeing that. Sorry about that. Analytically, I care. It's unfortunate. I will repeat this, because the relationship between omega L and sigma allows me to solve the Dirichlet problem for a function f that is in LP. Okay? And so that's important in this field. So that's why, so you see from our point of view, there was a geometric interest and there was an analytic interest. And maybe the question is, do these two interests coincide or the properties are very different, okay? So let me tell you what the relationship between two measures is. If you took a real analysis class, you saw these, but not required. And this slide is one of those slides where I'm going to ask you if what comes after these, which I will read this in a minute, but if what comes after these is above your head, close your eyes, and just look at something that's even, listen to my words, okay? I'm not going to read what it says there for the next one. So we say that omega L is absolutely continuous with respect to sigma if a set of measures 0 for sigma is also a set of measures 0 for omega L, okay? So if a set is not seen by sigma, then it's not seen by omega L. That's easy. But remember, I am interested in quantitative notions of everything. So I want a quantitative notion of absolute continuity. And basically, it says that if, I'm going to not touch that so I can tell you. It says that if a set is small, has a small measure with respect to another one within sigma, the same thing happens for omega L, okay? That's what this complicated thing, which you should read if you're not in the area, just read quantitative absolute continuity, and think of it, the condition I like, we call it omega L is an A infinity weight with respect to sigma, okay? But it's just a way to say that sigma truly dominates omega L. It's a very important notion in harmonic analysis, and in fact, it's what's called a Mac-Hout weight. Okay, so from the harmonic analysis point of view, this is a central object. Okay, so one of the things I would like you to reflect for a minute is that the geometric question, I said, this is the gold standard for regularity, because in geometric measure theory, that's the gold standard. In some sense, being an infinity weight in this field is the gold standard. And what we're trying to see is, do they correspond in any way, or is it just a coincidence that we were just stubborn? Okay. So here are the questions. If L is the Laplacian and omega is the harmonic measure, for what types of domains do I have that omega is an infinity? And if I know that I have a domain which is uniform and alphas regular, what does the fact that omega is A infinity imply about the geometry of omega? Can I say something else? And check it out. I wrote the same thing for the other operators. And you might be thinking, why? Such a short talk, how can she waste time writing the same thing twice? Because the answers are very, very different. So when you took a PDE class, they always told you that the theory for the Laplacian and for any divergence form second order elliptic operator were the same. In this area, that's not the same, okay? So now I need to talk about the Laplacian, and then we'll talk. So the case of the Laplacian, remember the homogeneous media. David and Jerison, and then separately Sems, proved that if omega is an alphas regular uniform domain, okay, that has the ball outside, then the harmonic measure is an infinity weight. So the harmonic measure is good. Okay, so that's one implication. First, there were two bullets of questions as the first question. What about the other one? Well, it's also true. Omega is an alphas regular uniform domain. L is the Laplacian. Then omega is an A infinity if and only if the domain satisfies the exterior corkscrew condition. So these two conditions are the same. Now, this is the work of a number of people through a number of years. Okay? And so what has happened in this area is that things were always proved first for the Laplacian, and then people started trying to prove them for the other operators, and people ran into trouble. Okay? So The reason was that Caffarelli, Phelps-Koenig, Modica-Mortola, and Salsa produced examples of operators on very nice domains where omega L and sigma were mutually singular. And that means they're as far as being mutually absolutely continuous as it can be. Who cares what singular means? It means really not absolutely continuous. Okay, so that meant that, that's a problem. So can we characterize the operator L for which omega L is an infinity? Does the characterization depend on the domain? And does the fact that omega L is an infinity say anything about the geometry? Okay, so this is 1982. The reason this appeared is because Dalbert had already asked a question, and the things appeared, and since there, people started working. And there have been many approaches. I just put them here so you realize that this is really something that we've worked a lot on. There's perturbation theory, structure of the matrix A, oscillation, properties of the solution, properties of the domain. There are many, many approaches. I'm going to focus on one. And I'm going to focus. So the oscillation approach, and we are going to look at, the DKP operators. They're called Dalbert, Koenig, and Pfeiffer operators. If this is another slide, if you don't want to look at the content, just think, she's going to put they put some conditions on the oscillation of the operator, of the matrix A. So we're asking that the matrix A be Lipschitz, and that its size is 5, a Carlson measure estimate. If this doesn't mean anything to you, please ignore it. It means that there's an integral condition that's satisfied. But it tells you we control the oscillation of the matrix A in some sense. Okay? And what Koenig and Pfeiffer proved was that if we had they had a Lipschitz domain and L was a DKP operator, then omega L was in an infinity weight. And then combining these with the work of David and Jerrison, and fair to say the work of other people that, like for example, Hoffman and Martel, we know how to show that on an Alford regular uniform domain satisfying the corkscrew condition, the same thing is true. Okay? So the question we want to answer is whether DKP operators predict the existence of a corkscrew balls, okay, on an Alford's regular uniform domain. So what am I asking? I'm asking, you have these domains, okay, basic geometric hypothesis. You know something about the elliptic measure, how the elliptic measure works with respect to the surface measured, and can I predict the existence of a ball, okay? Okay, so let me show you my collaborators. I'm going to try to keep the suspense as long as possible. Normally, you put the line of collaborators. Here are my collaborators. So there's Steve Hoffman, Chema Martel, Svetlana Mayboroda, and Zihu Sao. Both Svetlana and Zihu are here. And there's a cheetah. The cheetah is from the Canberra Zoo. The reason I put it there, unfortunately, that picture with the cheetah was not taken the day this happened. The first time Chema, Martel is Chema, heard me talk about anything having to do with these was at a meeting in Canberra in 2009. He had a number of questions. We talked, and then he started talking with Steve at the conference where the cheetah was. Well, the cheetah wasn't there, they went there. Svetlana wanted me to let you know that she also has a picture with a cheetah. But and so what did we prove? And why did I put the picture? Because, you know, teams of mathematicians look different. I want you to see what my team looks like. And so we proved that if you have an Alford's regular uniform domain and L is a DKP operator, omega L is an infinity if and only if exterior corkscrew balls exist. So this geometric information is also can also be extracted from these operators. I want to say one slide. Don't worry, I'm not going to do the proof. I want to say something about the proof. The proof took a very unexpected route. I think that's why we liked it. We had to first consider the case where the oscillation of the coefficients was small, and this was a GMT argument, something it was not something extracted from GMT, but philosophically, yes, extracted from GMT. Then we needed to use an extrapolation argument, similar to the one that Chema, Svetlana, and Steve had used before, that allow us, it's a general pathway to improve scale invariant smallness. So we had a small result. We needed to be able to translate it to a large result. So we had a machinery, but something happened along the way, and we needed to find a transfer mechanism to transfer. If you think I said that I am very, very happy when I have a small domain, that inside my domain I can put small Lipschitz domain, and it's basically because we know how to transfer properties from small Lipschitz domain into the big domain, but we needed a mechanism to transfer the properties from the big domain into the small domains inside, and so we needed a transfer mechanism. So we enjoyed, actually I think we enjoyed this work a fair amount. And now why, so this is the proof, and why we were happy. Because, so let me wrap around. I said I have these model domains. Can I distinguish between them? I want to finish by answering the question I asked at the beginning. The answer is yes. The DKP operators distinguish between Alford regular domains, for example, with the exterior corkscrew, they distinguish between a smooth or a Lipschitz domain and the exterior, the four-corner Cantor set. This provides a complete classification. It provides a quantitative analog of the Wiener condition, of the LP condition, and using the examples of Modica Mortola and the computation of a student of Svetlana, Bruno Poggi, we're able to show that this is an optimal condition. So we were very happy with what we did. Plus, we think we had a lot of fun doing it. And so let me finish here. Thank you for your attention. We have 3 minutes.
Okay, thank you, Tatiana, for this very nice talk. Do we have any questions? Yes, please, you can come up to this microphone.
Sorry to keep you in suspense. That was a little bit more of a walk than I figured on. So that was a very, very interesting talk to me. I work in some of those things as a graduate student, and I was wondering if you're aware of any work in that area in maybe Carnot groups like the Heisenberg group.
It depends what you mean in that area. If you mean in between the relationship between the PDE and the geometry, not exactly. If you mean into the geometry, there are some things. But even, the Carnot group is slightly different. The geometry changes things. But even if you, and it's not exactly the geometry given by the heat equation, but it's closer to that. But even if you were going to ask some of these questions for the heat equation for domains that are, suitable for that, then there's not answers. Okay, things are way more difficult.
Yes, they are.
So there's something where some things are done, but not that much.
All right, thank you.
Do we have any further questions for Tatiana? Yes, please.
Does looking at the spectrum of any of these operators give you any of the same information looking at the measures gives you?
So if you had asked me this question roughly 10 days ago, I would have said, you know, I have no idea. It's not that I have an idea, but something happened recently that has made me realize that very little is known, at least in terms of the behavior of the spectrum and the geometry of the sort of geometry I have of the domain, and that it might be an interesting question. It might be that we don't need to start looking at such a complicated thing. There's some smooth things that we don't even know as well. Okay, but it's a very interesting question. Thank you.
At the end of your last slide, you mentioned that the DKP condition is optimal.
Yeah.
Could you talk a little bit more about that? I was just wondering when, if there are cases of domains where the converse of the result that you mentioned holds.
So let me start by talking about the optimal part. So the DKP condition tells you that you have a bound on the Carlson norm. This bound on the Carlson norm is the thing that on a Lipschitz domain, the bound on the Carlson norm gives you a bound on the A infinity constants, okay? And if you look very carefully at the modica mortola and salta examples, what happens is you can construct examples where that constant starts growing, and therefore the A infinity, the constants degenerate, and for the limiting operator, you have an operator that satisfies all the other properties, except that doesn't satisfy the Carnot thing, and is a singular operator. Okay, so if it's not, this is not to say that there might not be other conditions, but this condition is necessary. Okay, that's it.
I think we're now out of time, so if you have any further questions, please ask Professor Toro during the break, and please join me in thanking her again for this beautiful talk.